Disappointment number one. I see three objects. Do you see three objects? Object number one, object number two, object number three. Three objects. Object number three is a bar spun about its center. Object number one and two are point masses spun about a distance L/2 from their center. That's squared, by the way. Factoring out the ml squared, I get 1/12 plus 2 times 1/4. That's a 12th plus a half. And a half is 6/12, so that would make that 7/12 ml squared. Now, let's deal with your deeper question for just a moment. I didn't give you the shape. Give me a shape. I don't care which one. Pick. What are those balls? What are they shaped as? Pick something. Solid spheres. Okay, so they are solid spheres. And that means I would have to use the formula I parallel equals 2/5 mr squared plus ml/2 squared to shift their moment of inertia, right? All right, let's say that we do this, and we don't know what r is yet, but we do know that r is less than L, correct? Just by the picture, that has to be true. So there are two of them, so 2 times I parallel. That's going to be 2 times 2/5 mr squared plus what I see is 1/4 ml squared. Good so far? I'm sorry, quantity squared. Let's just consider the picture. Maybe L is what? 5 times bigger than R? Just the picture? And I'd say it's more like 10 times bigger than R, wouldn't you? Just comparing L and R. Give me a comparison. A 1-to-5 ratio or a 1-to-10 ratio? 1-to-10. All right. So that means that R is 10 times bigger than L. Good so far? I want to make a comparison. So I'm going to substitute 1/10 in for R. 2 times 2/5 ml/10 squared plus 1/4 ml squared. Trying to see, okay, we're going to treat it like a real sphere to see how big an impact that is. 2 times L/10 squared will be L squared over 100, right? And it's a sphere, so it's 2 ml squared over 500 plus 1/4 ml squared. Just doing the math. That's all we're doing here is doing some math, trying to make a comparison. All right, so I can cancel that and get this over 250, right? Is that okay? So let's get common denominators. And that common denominator would be 250. That'd be 1. How many times does 4 go into 250? Help me out. I'm doing this for your sake. 65. I think 62.5. So plus 62.5 ml squared, all times 2. So that looks to be 63.5 0.5 over 250, right? Times 2 is going to be 127 over 250. Right? I'm just doing the algebra in my head on the fly, so help me out. This is now the moment of inertia of both spheres. Now, before we did all that, I'll remind you, we treated them as point masses. Do you remember what their contribution was? It's right over here. It was 6/12, or 1/2, right? 127 over 250. How close is that to 1/2? 125 over 250 would be 1/2. Does it make a difference to treat them like solid spheres? Do you see how close these two numbers are? Do you see why it's okay once we have our axis outside the object that maybe we could ignore their shape? I mean, if you don't believe me because you don't understand how numbers work, not really interested in helping you out. I gave you a rule, follow the rule, okay? And the rule works. If they don't tell you the shape, it's because it won't matter in the end. And it doesn't. You do see there's very little difference between those two numbers. And I'm still looking at people's faces, and they don't know why I'm comparing these two numbers. Sorry. But I'm comparing them on, and for you guys who do get why I'm comparing them, do you understand now? Okay. So, yeah, I don't care what the shape is. Once we have our moment of inertia outside the object, unless the problem is trying to be facetious, there's no reason to worry about it. I is 7/12. You should be moving on now to probably something about net torque equals I alpha, or net force equals MA, or in this case, M1A. In this problem, like I said, we just performed it. We just showed all the differences. But what's the torque? I don't know. There's a tension acting at the side of that spindle. That's the torque on the spindle. Everybody in agreement there? Is that what you put on yours? Because torque is the torque arm times the force times the sine of the angle between the torque arm and the force. The torque arm is however wide the spindle is. I told you to use a lowercase r for it. That's what we're using. And what's applying the force? The tension in the cable. I don't know what the tension is, but I know I can put it there. And that has to equal, well, 7/12 ml squared. Or whatever you get when you add 127 over 250 plus 112. Good luck for all of you, but I'm doing this one. And then times alpha. Now that has to corroborate with what happens to the mass. Right? The mass is creating the tension in the cable. It's a combination of the mass and the inertia of the bar. So what's happening to the mass? Well, gravity's pulling down, tension's pulling up, and that has to equal MA for the mass. Anything new here from yesterday? Because I'm thinking not a bit. Now, here's the next question for you. Do you want to find alpha or do you want to find A? Pick one. I don't care. Pick one of them. Okay, we're finding A. If that's true, then I have to find a way to express this in terms of A. So you have to ask yourself, how is alpha related to A? Can I use A equals alpha times something? And if so, what something should I put in there? L certainly makes no sense at all. Does the string wrap around something that is L long? Does one rotation yield a circumference related to L? Does R make sense? Does one rotation change the height of the mass by a circumference of the spindle? I think that does make sense, right? If you don't believe me, since we're solving this for A, I'm going to do that substitution right there. So RT equals 7/12 ml squared times A over R. And that has to equal M1G minus t equals m1a. We good? Now it's just substitution. I'm going to get the r by itself. I'm sorry, the t by itself by dividing both sides by r. R does not cancel out here, by the way. Sorry, but that would only be the case in problems where maybe the size of the object is the size where the string is attached. That's not the case here. You can't expect it all the time. That's just convenient. In fact, this is the case where nothing cancels out. So I do my substitution and I get m1g minus 7/12 ml squared a over r squared equals m1a. Icky, but it's just math. I want to solve this for a, so I get the things with a on the same side. So m1g equals, and I love just taking lots of space for this. You guys who try to hustle up all of your, your steps, don't. It's not helping you. Everything that's on the numerator there is 7 ml squared a, and everything in the denominator is 12 r squared plus m1a. Now, I'm likely to factor out those a's, I think, for obvious reasons. So 7 ml squared over 12 r squared plus m1 all times a. This is how you solve for a, right? Step by step, simple algebra. Doesn't matter to me how many letters there are. Algebra has rules. Follow the rules. Don't be scared. Divide both sides by whatever's in front of a. So a equals, well, m1g way up on top, and a collection of what looks like completely dissociated numbers and letters on the bottom. Algebra. I won't say basic algebra, but I will say algebra. Good so far? I think there's some obvious things that rear their heads here and some less obvious things. For example, L. Changing L is going to have a significant impact on the answer, isn't it? When I brought those masses closer together, I am making L smaller there. Maybe not for the bar, but for everything else. And the bar was only 1/12. Remember, the other thing is 1/2. It's a much bigger part. You understand what I'm saying? So when I make L smaller, I make this whole number smaller. And it's squared, so it's a big impact on that number. So does that corroborate what happens when we make L smaller there? Did it spin faster? Because when L gets smaller, the entire denominator becomes a smaller number. And therefore, it must accelerate faster. I think that's what we saw. Notice R. When R gets bigger, this number gets smaller. Is that what we saw? Sure is. Why? We have more torque on that one, right? We're pulling in such a way that's more effective because we're getting more torque. I expect it to be faster. It's squared even. Big impact there. Interesting. How much of an impact do we have if we change the mass that we hang? We tend to think of that being the biggest impact. It's the least important one, isn't it? Let's see it. I mean, that one seems so crazy, but it's got to be true. So this is 500, and we just watched it, but people don't believe me anyways. So watching it again. Oh wait, we'll count. We can count. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. Okay, so about 5, a little more than 5. So let's change that sucker. 1/5. And went from 500 grams to a solid 100 grams. Starting at the same place. Ready? 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6. It's a little different, not by much. So I think everything is there with purpose. right? All of those things affect the motion of how this behaves. Nothing canceled out because under this solution, everything played a role in affecting how the answer worked out. Now, if you ask me if this is a reasonable quiz, the answer is yes. 1,000 times over again, yes. There's nothing here that was new except that you had to build a moment of inertia, of which I think it was okay. So, hopefully this is good review. You guys see how this problem can kind of play out. If you did not do really well on it, okay, well, this is our first time going through it. It takes some time.